All right, guys, we are here today and having a little bit of technology issues this morning, but I think we're ready to go. And we're going to look at some more of these problems of the spherical mirrors. Okay, so I wonder where that glare is coming from. Oh, that's going to be straight above. All right, so here we go. Let's go ahead. I think last time we did go through problems 1 and 2, and then we still want to go through problems 3 and 4, if I remember correctly, for 13b, and we never went over those. All right, so I want to go ahead and do that. We'll go over problems 3 and 4 together. If you guys have any questions, feel free to ask me there in the chat. And I'm thinking we are probably, let me think, probably shooting for a test sometime next week, I'm thinking. So I'm just trying to go through this in my head exactly where we are in terms of the time. So I think we got, I don't remember how many more sections this particular chapter is, but I'm thinking shooting for maybe a test sometime next week sounds pretty reasonable to me. Okay, so just keep that in mind. Let's go ahead and go through number 3 here. We got a concave makeup mirror, right? And so we remember concave mirrors are these mirrors that are kind of like they're caving in on you. That's going to be way, way exaggerated, but it's like a spoon, the part of the spoon that you can eat out of. So that's like your concave mirror. The backside of a spoon is going to be a convex mirror. All right, so we have a concave mirror and concave mirrors, and we should say in general. I want to speak about some of these things in general too. So I'll write it down here in a bit. Concave mirrors are able to make things look larger, but sometimes things will look smaller in a concave mirror. In a convex mirror, things will always look smaller, okay? And so that's going to be a difference between concave and convex mirrors. So it's designed so that the person 25 centimeters in front of it sees an upright image at a distance of 50 centimeters behind the mirror. And so we can say, well, right now, that's going to mean that we have a magnification of 2x, right? So we have Q over P is going to be a magnification of 2x. And we'll talk about specifics here in a little bit. What is the radius of curvature of the mirror? So we're actually solving for R in this case. What's the magnification? And is the image real or virtual? So let's just go through the numbers. We don't actually have to do the drawing if we don't want to. But you know what? I'm going to go ahead and just do the drawing. But it doesn't require you to do the drawing for this particular question. So as we read through it, let's see if I can do this side by side. And we can say in general, a convex mirror is going to be, let's turn this on, always smaller images, whereas a concave mirror is going to be is going to depend, right? It's going to depend on the specific situation, right? And so it's going to be sometimes smaller and sometimes bigger. All right, now back to number 3. Number 3, here we have a concave makeup mirror, a person, so we have our P is going to be 25 centimeters in front of it, and it sees an image. It's an upright image at a distance of 50 centimeters behind the mirror. So because it's behind the mirror, our Q is negative 50 centimeters. You're like, Mr. Ketz, where's that negative come from? The negative comes from the fact that it is behind the mirror. That is why this is negative, and negatives are important. It's not like, oh, it doesn't really matter. Yes, negatives do matter in these, all these images. Mirrors, lenses, they do matter, very much so. Okay, so that negative means it's behind the mirror, and you notice it also says that it's upright. Right? What does upright mean? Upright has nothing to do, well, actually it is related to whether it's behind the mirror or not, but that's a separate issue. It's upright, and so because it's upright, we know that M is positive. It's got to be positive, Okay? And what else do we know about it? I think that's pretty much it, right? We know those two things. So let's go ahead and first, like I said, I want to calculate the magnification first because that makes the most sense. The magnification is negative Q over P, and we see that the magnification is negative, so it's negative 50 centimeters over 25 centimeters. So that's going to be 50 divided by 25 is 2. Negative and negative is positive, so it's going to be a magnification of 2x, or m is 2. Isn't it virtual too? Yes. Right. Because it's behind the mirror, that's going to mean it's virtual. That's correct. So what else is this? So it says, what's the magnification? Is the image real or virtual? So we've answered two of them. This is the magnification. Yes, it's virtual. Last of all, it wants to know what's the radius. So that's involving a calculation. So I'm going to go ahead and just do that one last, right? So that is going to be 1 over P plus 1 over Q equals 1 over F. So we can calculate F. And so that's going to be, move this over now, 1 over 25 plus 1 over negative 50 equals 1 over F. And we're going to solve for F first. And then we can calculate the radius from F. So in this case, I would just, you can do this however you want. So you could do this in your calculator, or you could do this in your head. 1 over 25 is going to be 2 over 50. So 2 over 50 minus 1 over 50 is going to be 1 over 50, right? And then you take the inverse of that. And so we're expecting an F value of simply 50 for this one. But let's just do the math just in case in your calculator, we're expecting an answer of 50. Okay, so 1 divided by 25 minus 1 divided by 50, get our answer, right? And then we're going to do the inverse of that. And oh, look, we were right. That is 50. F is 50. F equals 50. Now, F is closer to the mirror than the center. So remember that the radius is equal to what? It's equal to 2F, or F is equal to 1. F is equal to 1/2 of the radius. So the radius is going to go ahead and be 100 centimeters. Okay, so that's number 3. And we can draw it if you want to, but there's no real need to, because we really started off with P and Q rather than starting off with F. So it doesn't really make sense. You know what, I'm not even going to, if you guys want me to draw another drawing, I can draw it. But I think I'm not going to bother. Okay? All right, number 4. Number 4, what do we got? We have a pen, which is going to look like a tree, because I want it to look like a tree. A pen is placed 11 centimeters from a concave spherical mirror. So right away, that's going to tell us what your value for, let me see how I'm going to do this. Let's do it upside down. Here we go. That's going to tell us the value for P, right? So it's going to mean P is 11 centimeters. And it's a concave spherical mirror, like every one other problem here. And it produces a real image. So that tells us that your Q is going to be positive because it's a real image. That's 13.2 centimeters, 13.2 centimeters from the mirror. So we have the value for P and Q, both of them being positive, right? Well, what is the focal length of the mirror? What is the magnification of the image? Let's go ahead and calculate those. Magnification is going to be negative Q over P. So 13.2 centimeters over 11 centimeters. Let's calculate that in here first. (13.2) divided by 11 gets us 1.2. So a small increase in size, 1.2. And what else do we have to do? We have to figure out what is the value for f. So we have 1 over p plus 1 over q equals 1 over f. So that's going to be 1 over 11 plus 1 over 13.2 equals 1 over f. And so that we're expecting a somewhat of let's just see what this is. Somewhat of a smaller number, I think. 1 divided by 11 plus 1 divided by 13.2. And we get this. Oh, that's nice. This is going to work out nicely. So we take the inverse of that, and it's going to get us f is 6. Oh, so they chose these numbers pretty nicely. So f equals 6. Okay, and that should be 6 centimeters. So what else do we need to know? We've got the focal length, 6. What's the magnification? 1.2. And we know that this is, we already know this is real, and we know that the magnification, so this is, I'm sorry, I deleted this negative for some reason. This magnification should be negative 1.2. And so because the magnification is negative, it should be upside down, right? Or let's call that inverted. Inverted means upside down. And what else do we need to know? New position, magnification. And we already said that this thing is real. So let's go. Okay, what's so if the pen is placed 27 centimeters from the mirror, so we're going to change this. So this is nice. We got like more than one problem in one problem. So we have the same focal length. Now, if the pen is placed, so we have a P of 27 centimeters from the mirror, what is the new position of the image? So let's solve for Q. 1 over P plus 1 over Q equals 1 over F. So that's going to be 1 over 27 plus 1 over Q equals 1 over 6. So what we're going to do in our calculators is going to be 1 over 6 minus, let me see. It should be, where is it? 1 over 6 minus, where was it? 1 over 27 to get you, this is going to be 1 over Q. And then we're going to take that and we're going to flip it. So 1 divided by the answer is going to be the value for your Q, 7.71. Q, 7.71. And in this case, it's still going to be a positive number. So when you calculate the magnification, we're expecting another negative number for that one. But in this case, it's going to be smaller, right? 7.71 divided by divided by 27. And that's negative. Divided by 27. And we're getting out of a fairly small thing. So 0.286. 0.286 negative once again. So our magnification in both these cases is negative, which means we're expecting something that's inverted. In both cases, real image. So inverted and real, and also in this case, it's going to be smaller. In fact, much smaller. And so we're going to go ahead and try to draw this on here. I think I got space to do this. Let's see. Let's try to draw this right over here. Move this out of the way. Sorry about that. And let's use a straight edge. So we have our principal axis right here, and on the principal axis, we're going to go ahead and put our concave mirror. Now, it's important for us to keep these numbers in mind that they're approximate. We're not going to be able to draw this exactly to scale, so they're approximate. Let's go ahead and try this. So we have a P of 27 and an F of 6. So really, this image, or this object is very far away from the focal point. And so let's just go ahead and write something. So this, we're going to make this F, make this the center. So this is F, this is the center, and that is going to be 12. So this is going to be 24 right over here, and it's even further away than that, a little bit further away than 24. So it's like right about there, and that's going to be where I'm going to draw my tree. And I'm going to go ahead and draw my tree fairly big. At least I'm using up as much space as I can here because I know already from our predictions that this is going to be pretty small, right? It's going to be inverted and it's going to be small. So let's go ahead and try this out. So we're going to start with something. I'm going to go parallel in and then out through F, and then I'm going to go through the center. I feel like those are going to be the easiest ways to do this. So take my light ray and try to make this as straight as possible. Parallel in when you hit the mirror, then we're going to go through the focal point out. Like that. Parallel in, focal point out, and then we're going to go through the center and through the center. Okay? And notice that each of these times we're starting always going from the top of the tree, from the top of the object. That is what we're looking at. Because the bottom is always going to be on the principal axis. Okay? And so the next one is just going to go from the center to the center. Like this. Center. And it's going to go bounce in, bounce out. That's where your light ray is going to go. And where those two reflected beams cross, that's where your image is. And let's see if this makes sense. Well, first of all, we notice that's going to be super small. It's exactly what we'd expect. It's going to be upside down because it's intersecting on the other side of the principal axis. And it's going to be real. Why? Because it's on this side of the mirror. So all those things concur with what we did through the number side, right? So we got something, images small, inverted, and real, right? And let's also figure out, okay, what is Q for this one? Q is 7.7, about 7.7 centimeters, which is a little bit bigger than F, and that makes sense. Remember, F is 6, and so this number here should be about 7, 8-ish, right? Which makes sense. So that drawing makes perfect sense for the numbers. And I think that's pretty good, okay? So, any questions on these? I saw if there were some questions that were going on and I didn't really get to them because I was kind of like just going through the problem. And I think, yeah, virtual, yes. Isn't negative, yes. For the magnification, if it's real, it should be yes, it's real, and yes, it's negative. Okay? Any other questions? Nothing. All right, let's go on to the new stuff then. I know some of you guys have already read ahead, which you're awesome, but we just, I just wanted to take time to do this, and so we wanted to, this homework assignment for your convex mirrors is not going to be due until tomorrow. So I know I gave it to you guys back on Friday, but I'm not going to make it due until tomorrow, and we're going to go ahead and talk about that today. The nice thing about these convex mirrors is really, it's all the same equations, okay? The main difference that you're going to notice is that for your convex mirrors, that your things are always going to be, so convex. Right? They're always going to make them smaller, all right? And it's always going to end up being, so always smaller, right? It's always going to be upright and is always going to be virtual. So it makes it a little bit easier for these, all right? And let's go ahead and try some out. I believe this is known also as a diverging mirror, although that term I believe is used more often for the lenses than it is for the mirrors. So this is a convex mirror. So let's go through a sample problem and see how this works. It should start to get easier now that you guys have done all these. We had a couple days to do the concave mirrors. You get 1 day to do these convex mirrors. All right, sample problem C. We have a pencil once again, so a tree-looking pencil. It's going to be placed in front of a convex spherical mirror with a focal length of 8. Right, and our focal lengths for these it doesn't say this, but and I should have mentioned this earlier, because it's a convex mirror, your focal length is going to be negative. Why is it negative? So let's go -8. The reason is when you look at the mirror, the focal length is going to be on the other side of the mirror, right? So if you have this, let me do a partial drawing here. If you have a principal axis here, and you have a mirror like this, if you were thinking, so let's make, and I'm going to try to figure out what are some of these numbers here. So if we were to make the the focal point right here, if this is F, right? If this were a concave mirror, then your light would be coming in here and bouncing off and then going through the focal point. But you know what? It's not. The light's on this side, and this is where the mirror is. So because the focal point is on the other side of the mirror, the focal point is on the La La Land, the no man's land, over on the other side of the mirror. That's going to give the focal length always a negative value. All right, so it doesn't necessarily tell you, okay, the focal length is -8. It's just because it tells you this is a convex spherical mirror, therefore you know that that's actually got to be a -8. All right, and that's going to mess up all your numbers if you get that messed up. Okay, so F is going to be negative. And erect image of 2.5, so it's a rect image, so we know, let me see, 2.5 centimeters tall. Oh, look at this. This time we're actually going to get the image height is formed 4.44 centimeters behind the mirror. So we have, in this case, a value for P is, no, I'm sorry, that's the image, right? Image. P is, do we have P in this one? I don't think we have it, right? So Q is -4.44 centimeters. And we're trying to find the position of the object. We're trying to find that, which is kind of a strange way to solve a problem like that, because normally you know the position of the object, but you just don't know the other stuff. But anyway, so we're solving for P, and we also know that the image height is going to be 2.5 centimeters tall. All right, and so we're also going to probably solve for the object height. I don't know. Solve for the position of the object, the magnification. We want to know magnification. And we want to know the height of the pencil. And that's going to be the last thing. Object. Okay? All right, so there we go. That's our problem. A lot to do. So we have a value for F, we have a value for Q, so we can go ahead and solve for P, which must be positive because you can't have a negative value for P. The object has got to be in real land. It can't be in no man's land. So 1 over P, I can fit this in here, plus 1 over Q equals 1 over F, same equation. And so we have 1, and we don't know P, right? So 1 over P plus 1 over -4.44 equals 1 over -8. And let's go ahead and plug in the numbers in our calculators. I'm going to add this to both sides. So I have a -1/8 on the right side. And then I'm going to add this to both sides. So plus 1 divided by 4.44. This is going to give me a positive number, about 0.1. So we're thinking about 10, right? Or 9 point, yeah, that's about 10, 9.98. P equals 9.98. Once we have that, let's go ahead and calculate the magnification. Magnification is -Q/P, which should be positive, and it is because we have a Q value which is negative. And so your magnification is -4.44 divided by 9.98. So that is going to be a positive number, which is, oh, look at that. It's a nice, yeah. Wow, that works out to be very nice. 0.445. 445. I forgot units on that one. Don't forget your units. That's going to be centimeters. Magnification has no units. Your P and Q are going to be units in centimeters or some kind of other length units. And once we have that, we can calculate the height of the object, because we remember that your magnification, the actual definition for your magnification, although we're used to the equation of -P/Q, the definition of magnification is actually the height of the image over the height of the object. And if we want to know the height of the object, we're going to flip these two, right? We can just multiply both sides by h object and divide both sides by m. That's going to get us h object. It's going to be h image divided by m, which is, your object is, that was 2.5, right? 2.5 centimeters divided by 0.445. So 2.5 divided by 0.445 is 5.6. 5.6 centimeters. Okay, so that's your answer there. That's all of the math, right? And does it make sense? Yeah, so it makes sense that you have the object is bigger than the image, and that's going to be true for all of these. Your convex mirrors always make things smaller, and they're going to keep things upright, and they're always going to give you your virtual images. And let's go ahead and do the drawing for these, because the drawings for these can be sometimes a little bit trickier. But let's make sure we have kind of realistic numbers here. So if this is a -8, right? That's our focal point. And remember, the center is going to be over here too. So if this is the focal point, then the center is way over here. Here's your center. And what was my number for Q is -4.44. And so that's, and it's upright too, right? And so we're going to be putting it, this is kind of weird. You know what? I'm going to do this thing starting not with the Q, but starting with the P. I know it's kind of, you had to solve for it first, but let's see where it puts our image, because it doesn't make sense actually to do these drawings to solve for Q. So let's just do a, I don't even know if it tells us to do it. So anyway, I'm gonna do a drawing of this particular one, and let's use this value of 9.98. So if F is 8, we're thinking something of like bigger than that. And so this is kind of the sketchiest part of these sketches, is just figuring out exactly where this is. So I'm thinking right around there. Let's do that. That looks good. I know it's a pencil, but I don't like drawing pencils. I draw trees. Okay. So for our drawing now, for this convex mirror, what I'm going to do is, what you can do is you can do either parallel out, focal point, parallel in, focal point out, or you can do focal point in, parallel out. I'm going to go ahead and do parallel to start with. And so we've got some light that's parallel. And this is where it's going to get nice, a little bit different here. So make sure you actually do these drawings. I don't think it says to do drawings on some of these, but please do drawings for these, okay? You're never going to be able to do the drawings if you don't practice, okay? So we got parallel in, and then you're going to go through the focal point out. But notice the light is bouncing out. It can't ever go through the focal point. It's impossible for it to go through the focal point. So what gives? How do I actually do this? So the way you're going to do it is you have out here in La La Land, the light is going to be coming here. And then once you get to the mirror, this is how it's going to bounce out, right? So the light is coming in parallel and then out through the focal point. Yes, it's never going to actually go through the focal point because the focal point is on the other side of the mirror. So this is going to be how we're going to draw that. And then the easiest one always to do is the center. At least in my opinion, almost always the center is the easiest one, unless the object is specifically on the center, and then things get a little bit weird, right? But it's not. You can't have an object on the center for one of these convex mirrors. So what I'm going to do is I'm going to come and, this is hard, come here. Once I get to the mirror, I'm going to just do dotted lines because the light isn't really going here. It's just the direction that the light is, right? So it's going to hit the mirror, then bounce right back. So light comes in like this and then goes out like that, okay? Light comes in like this and goes out like that. And then where these two things cross, that's where your image is going to be. Notice because this object will never be able to go between C and F or on top of C or F or on the other side of C and F. The object is always going to be over here. That's going to make these the light is always going to turn out to be a virtual image. And because it's a virtual image, it's always going to be upright, and it's always going to end up being, just due to this nature, it's always going to end up being smaller. Okay, so here we go. This is where my tree is. Okay, where these two reflected beams cross, that's where your image is. And let's see if it makes sense. So we had an f of -8 and we had a q of -4. Well, I kind of must have not drawn this perfectly, because I'm thinking 4.44 should be more or less like right over here. And so I probably just messed up in my drawing. So sorry about that, guys. And it's probably the main problem has got to do with where exactly you put this, and also, you know, how good a job you do at making these things parallel. But anyway, so it's pretty close, right? It should be at -4.44, but it looks like it's more like -6 or something. Hey, whatever, right? Sorry about that, guys. But this is kind of how it should look. Your drawing should always be more or less accurate in terms of more or less what we know approximately where it is, but it's not going to be perfect. At least, you know, not always. So what else? The magnification is a little bit less than half. Yeah, that looks like a little bit less than half of that. That looks pretty good for the magnification. Pretty good to me. Anything else? I think that's pretty much everything. That's it. We're done. We're done. All right? You guys got homework. I think a few people have already done it. If you've already done it, you're awesome. If you haven't, that's okay. It's not due till tomorrow. And please, please, if you haven't done them, if all you did was the math, please do the drawings too, okay? Take some time to actually do these drawings. I will make you do drawings when the test comes. I'm not just going to have you do math. You will have to do the drawings, okay? And so make sure you do the drawings, even if the question doesn't ask you. See you guys. I'm out. Any questions? All right. If there are no further questions, I'm just going to sign out. See you guys. Oh, one question right before I stop. So just follow those 3 steps. Yeah. Which 3 steps do you mean? There are really 2 rays that you need, right? You need parallel in and then bounce out through the focal point, or in through the center and out through the center. So I only draw 2 of these things, and that's it. But this is basically it. Different problems might have you solving for different things, but you know, it all works out to be the same. Whether you're solving for P, solving for Q, or solving for F, The equation is all the same. The main thing that you're really going to have to pay attention to is this, let's even make it this negative sign here, because the book doesn't tell you. And that gets a bit, can be confusing here. And that's where most of your mistakes are going to happen if you make the focal length as positive when it should be negative. The ones we covered last lesson. Yeah, so same steps, same things. But you only need to do 2 of them, right? And you can do any 2. You don't need to do all 3. Notice I only did 2. But you can do any 2. The other line, what would the other line have been? The other line would have been going in through the focal point. And I could draw it if you got a sec. Let me draw with a different color. Let's draw. Let's use purple. So the other line would be like this. It would be in through the focal point, and you only need 2. You don't need 3, right? But the other line, if we wanted to, would be in through the focal point, and then you're going to bounce out parallel, which is going to be like this. Like that. Okay? And notice that these kind of all intersected exactly more or less the same point, right? And because you only need 2 lines to have an intersection, you don't need to do all 3. Just 2 of them is fine. Is Q always going to be negative? Yes. It must always be negative for your convex mirrors. Yep. And P is always going to be positive. And F is always going to be negative for these, for convex mirrors. And for convex mirrors only. Concave is another story. And the reason just is simply because this object, you can't ever put the object in between C and F or on C or F. And so that limits your options here. That's why. Okay. Any other questions? All right. I'm going to go ahead and sign out then. I will see you guys tomorrow, and that's it. Have a great day.